Now suppose we have a situation where we have two curves. One looks like this, one looks like that, and we want to find the area of the region bounded by these curves, this region in here. And I somehow don't get a high-low feeling here. In fact, this first curve might be written as x equals f of y. This might be written as x equals g of y. These are functions of y, not functions of x. They would pass a horizontal line test, but not a vertical line test. Let's say this is y equals c, y equals d, two horizontal lines which bound the region. Still, I want f and g continuous on, instead of the closed interval AB, on the closed interval CD. And I want this time f of y greater than or equal to g of y for all y in the closed interval CD. Now, if I say f of y is greater than or equal to g of y, I mean the x value of this curve is greater than or equal to the x value of this curve. When it was y values, it gave me a high-low feeling. When it's x values, what does it mean if the x value here is greater than or equal to the x value here? I get the feeling that this curve is to the right of this curve. Instead of a high-low region, we have produced a right-left region. So when we have a right-left region, you draw horizontal lines, and every horizontal line seems to go from one curve on the left to the other one on the right. I'm going to, instead of having, once again, the formula for area, which would be c to d, the integral from c to d of f of y minus g of y dy. This is the formula that's in the textbook. I'm going to recall this. Instead of x equals f of y, I'm going to make this the x of the curve on the right. And this, I'm going to recall the x value of the curve on the left. So from now on, instead of f of y, I'll do xr of y. Instead of g of y, xl of y. Now, it is true that I'm using the same letter L that I used for high and low, but I think you will have no problem. If it's a high-low region between two functions of x, that's one thing. When it's between two functions of y, we're having a right-left region. Okay? This will be the x value of the curve on the right minus the x value of the curve on the left, dy. If C and D are explicitly given you, no problem. If they're not explicitly given to you, then very often they're going to be related to the points of intersection between the curves. And C is going to be the y-coordinate of the lowest point in the region. And D is going to be the y-coordinate of the highest point in the region. Let's try an example. C and D, remember, are y-coordinates of the lowest and the highest points. X, R, and XL are in terms of y. You integrate with respect to y between this y value and that y value. For our next example, find the area of the region bounded by the curves x equals y squared and x equals 2 minus y. Now, these are both functions of y. Your graphing calculator is not going to be as helpful here because it's basically set up to graph functions of x. You can, of course, exchange all the x's and y's, and you'll get a picture which is similar to the one, a region that has the same area as the region you're looking for, although it will not be exactly the same kind of picture. Let's see if we can do this on our own. X equals y squared is the parabola vertex at the origin opening to the right. X equals 2 minus y is a straight line. If y is 0, x is 2. If x is 0, y is 2. Looks something like this. And let's say I drew the curves, the region bounded by these curves. I wasn't sure. So the reason this is not a high-low region, although it could be split into two high-low regions, more about that later, but the reason it's not a high-low region is that here, if I draw vertical lines, I'm going from the line to the parabola up to this point, and then I'm going from the parabola to the parabola. In order to do this as a high-low region, you'd have to split it into two regions, because for each region, there has to be one high curve and one low curve. We can't have the high curve changing, but if we do it as a right-left region, every horizontal line goes from the parabola on the left to the line on the right, exactly the way we want it to go. So the x value of the curve on the right, that would be the line, solve for x, which it already is given like. The x value of the curve on the left is y squared. Now, y equals c and y equals d are the y coordinates of the lowest and highest points, which are really the points of intersection of these two curves. We could solve simultaneously by setting these two x values equal to each other to get y squared equals 2 minus y, or y squared plus y minus 2 is 0. We could factor y plus 2 times y minus 1 to get y equals 1 and y equals minus 2 as the y coordinates of these points. Y equals minus 2, y equals 1. X is equal to y squared, so here x is 1, here x is 4. Or x is 2 minus y. So 2 minus 1 is 1. 2 minus a minus 2 gives us a 4. But we really only need minus 2 and 1 for C and D. So the area, in this case, is going to be the integral from C to D, from minus 2 to 1, from the y value of the lowest point to the y value of the highest point in the region, xr, which is 2 minus y, minus xl, which is y squared dy. Now, I don't really need the double parentheses like I had before, because this is only one term that we're subtracting. Now, the calculator will give you this answer if you hit math and 9 and ask it to integrate 2 minus x squared with respect to x between minus 2 and 1. Doesn't care whether you're using this with respect to y or respect to x, as long as you're consistent all the way through. So let's see what we get for an answer here. Let's clear this all out. I hit math 9. We're trying to integrate 2 minus x squared, comma x, comma minus 2, negative 2, comma 1, close parentheses. And we get an answer of 4.5 square units. And this is what it's supposed to look like. Just want to mention that if you really cannot graph it, okay, if we hit y equals, let's clear these out. If you interchange the x's and the y's, if you ask it to sketch y equals x squared and y equals 2 minus x, okay, you don't get the same region that we got. But you get what you would get if you were to, say, write this on a piece of paper, pull it out, and hold it up to the light backwards so that the x-axis would be pointing up and the y-axis would be pointing to the right, because you've interchanged the x and the y-axis. Certainly there is a similarity between that region and this region, and if you could know how to go from there to there, if you worked on that at home, you would be able to sketch it in terms of x and then go back and get the correct picture. But you could copy this onto a sheet, and to understand that this really has the y-axis to the right and the x-axis going up, and then if you were to rip it out, hold it up to the light so that it's interchanged, then you would produce this picture, which is the one you really need. Okay, in problem number 6, I want to find the area of the region bounded by the curves y equals x, y equals 4x, and y equals 1 over x in the first quadrant. Let's graph these on our graphing calculator. We have y equals x. Enter y equals 4x. Enter y equals 1 divided by x. And I'll hit graph. That's one line, that's the other line, and that's the hyperbola, which would be in the first and third quadrants, but I'm really interested only in the first quadrant. Let me blow up the region involved. Let me hit zoom and decimal to get a little bigger picture in that first quadrant. Okay. So I'm looking for the area of this region. Let's just look and see what we have. We have y equals x, which is the 45-degree line, y equals 4x, which is going to be steeper, and y equals 1 over x. And we have 3 points of intersection, which can be found by solving these equations 2 at a time. In other words, y equals x and y equals 4x, solve them simultaneously, you get 0, 0. Y equals x and y equals 1 over x, solving simultaneously, you get x squared equals 1. X is plus or minus 1. The one we're looking for here is x equals 1, y equals 1. And y equals 4x solved simultaneously with y equals 1 over x. 4x squared equals 1, x squared is 1/4, x is plus or minus 1/2. The negative refers to the third quadrant, which we're not using. You'd get 1/2. Y would be 1 over 1/2, or 2. If you have difficulty with that, of course, you can do it on your graphing calculator. Second, Calc 5. I'm not even going to bother with the first one, which is the origin. Let me move it over to this point of intersection. I hit, well, actually, there's not much to do. I'm not going to go further because it'll be actually the point of intersection, so I'll pretend that I'm in that vicinity. Hit enter once, twice, 3 times, and it gives, oh, it gave me the wrong point of intersection, so I guess I shouldn't be such a wise guy. Second, Calc 5. If I hit, I guess it really wants you to use the fact that it does give you the point of intersection. First curves. Oh, it has the 3. It gave you, because I see, we weren't paying attention. We had 3 curves, and it only has 2 curves. So if you wanted to get that point of intersection, you're going to have to tell it which 2 curves you want. In other words, you want the intersection of y equals x with y equals x with y equals 1 over x. So we're going to have to go over here, lift the equal sign. In other words, hit the enter over the equal sign. So it says that the only 2 curves we're going to be sketching now are the y equals x and the y equals 1 over x, then when you hit graph, it'll give you just those two. And then if you ask it to do second calc 5 and send it over to that one, it would give you the right point of intersection. Enter, 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 and it would give you the 1, 1. So you have to be careful. Wasn't paying attention when you have three curves as to which ones you're asking it to plot. Okay, anyway, we can get all our points of intersection one way or another. Going back to y equals, you could have turned that back on. If you want all of the functions on, you hit the equal sign again, and that means all of them are active. And then, of course, you can graph it. It throws back the other function. Now, let's go over here. We've got a problem. We have a high curve of y equals 4x, a low curve of y equals x. It looks high, low, up until you get to this point. At this point, the low curve is the same, but the high curve has changed. In order to do this problem as a high-low region, you're going to have to divide it up into two regions, region 1 and region 2. The area is going to be the area of region 1 plus the area of region 2. What is A and what is B? In region 1, the high curve is y equals 4x. The low curve was y equals x. A and B are the x coordinates of the leftmost and rightmost points in the region. So from 0, which is the x coordinate here, to 1/2, which is the x coordinate there. In the second region, the high curve is y equals 1 over x, the hyperbola. The low curve is still x, but now A and B are 1/2 and 1, respectively. By the way, before I decided to do it high-low, I should have also tried right-left. Sometimes a region which doesn't work as a single integral high-low might work right-left, but here we would have the same problem. If we did it right-left, the curve on the left in both cases would be the line y equals 4x, but the curve on the right would go from the hyperbola here to the line y equals x here. So it would still necessitate a split at this level. So it turns out here you're going to have to use two integrals regardless. So in region 1, we're going to have the integral from 0 to 1/2, the y value of the high curve minus the y value of the low curve with respect to x, plus the integral from 1/2 to 1, the y value of the high curve, which was 1 over x, minus the y value of the low curve, which was x with respect to x. And you can work these out on your graphing calculators. And let's see. I'm just going to combine this as 3x. So function to be integrated, let's say 3x with respect to x from 0 to 0.5. And the function to be integrated, parentheses 1 over x minus x, comma 0.5 to 1. Let's see what we get. Second quick. Math. 9. The first one was 3x, comma x, comma 0, comma 0.5, close parentheses. 0.375 for this. And for the second one, math 9, left parentheses 1 divided by x, close parentheses, minus x, comma x, comma 0.5, comma 1, close parentheses, 0.318 something. Okay, 0.375 plus 0.318 for an answer of 0.693, or approximately 0.69. square units for the sum of the areas of these two regions. Last example on this tape, I want to find the area of the region bounded by the curves y equals x squared plus 2, y equals 2, and x equals 3. Actually, I want to do this region both as a high-low region and as a right-left region, and to show you that we do get the same answer, and I think it will help to reinforce the way that we do the two problems. Let's see what we have. Y equals x squared plus 2, of course, is the parabola y equals x squared, shifted up 2 units. Looks like that. Y equals 2 is a horizontal line going through 0, 2. X equals 3 is vertical line, and this is the region we're talking about. This particular region could be done as high-low or right-left. Actually, it's a little easier to do with high-low, but I think it'll be instructive to force ourselves to think of it both ways. Let's get all the points of intersection. Certainly, y equals x squared plus 2 intersects y equals 2, solving simultaneously when x is 0 and y is 2. Y equals 2 crosses x equals 3, obviously, at the point 3, 2. And last, y equals x squared plus 2 crosses x equals 3 at the point when x equals 3. And if x equals 3 in here, y would be 3 squared, 9 plus 2, 11. We're going to start off by doing this high-low. If we do it high-low, we need the y value of the high curve, the y value of the low curve, A and B, the x coordinates of the left and rightmost points in the region. The high curve is y equals x squared plus 2. The low curve is y equals 2. A and B. A is the x coordinate of the leftmost point in the region, which would be 0. B is the x coordinate of the rightmost point in the region. Anything on this vertical line would qualify as rightmost point in the region. Of course, they have the same x coordinate because they're on the same vertical line. So B would be 3. And the area would be the integral from A to B, the y value of the high curve minus the y value of the low curve, dx, the integral from 0 to 3 of x squared plus 2 minus 2 with respect to x. The 2's cancel. It's not too difficult to actually anti-differentiate and plug in to get 27/3 minus 0 or 9 square units for the area of this region. And we've done the problem. It's easier to do high-low than right-left, but I think you will learn a lot if we look at it right-left. Let's go over and do the problem over. Once again, we have the parabola and the 2 lines. We have these points of intersection. It's not exactly drawn to scale, but that's okay. We want to do this now as a right-left region. We'll need, to do this right-left, we'll need the x value of the curve on the right, the x value of the curve on the left, and C and D, the y coordinates of the lowest and highest points in the region. The x value of the curve on the right, that would be the line x equals 3. The x value of the curve on the left we had the parabola y equals x squared plus 2. We're going to have to solve for x equals. The region can go high, low, or right, left. You might decide which way you want to do it by, whether it's easier to solve for y or easier to solve for x. Right, left regions, you must be able to solve the equations for x. So here, y minus 2 is x squared. X would be plus or minus the square root of y minus 2. Now, in the first quadrant, this is x equals the positive square root of y minus 2. If the region were in the second quadrant, you'd be using x equals the negative square root of y minus 2. So the curve on the right is x equals 3. The curve on the left is the positive square root of y minus 2. C and D now are the y coordinates of the lowest and highest points in the region, 2 and 11. The area is going to be the integral from C to D, the x value of the curve on the right minus the x value of the curve on the left with respect to y. The integral from 2 to 11 of 3 minus the square root of y minus 2 dy. Now, if you do this by anti-differentiating and plugging in, you would get, anti-differentiate 3 with respect to y, 3y. This is like a u to the n du, y minus 2 to the 1/2. To anti-differentiate, you get y minus 2 to the 3/2 over 3/2 between 2 and 11. That's 3y minus 2/3 inverting and multiplying. Y minus 2 to the 3/2. 3/2 power means the square root cubed between 2 and 11. So here I divided by 3/2, I invert and multiply by 2/3. The 3/2 power means the square root of this cubed. I'm going to substitute in what I get at 11 and then subtract off what I get at 2. At 11, I get 3 times 11, 33, minus 2/3, the square root of 9 cubed. The square root of 9 is 3. 3 cubed, 27. When I substitute in the 2, 3 times 2 gives me 6. Here I get 0. So I get 33 minus 3 goes into 27, 9 times 2, 18, minus 6. 33 minus 24, once again, 9 square units. Now, I just want to show you a slight problem with doing this on the calculator. Let's do them both on the calculator. The first one, I wanted to integrate x squared from 0 to 3. The x squared plus 2 minus 2, so basically x squared from 0 to 3. I hit math, I hit 9. I integrated x squared, comma x, comma 0, comma 3. Close it up, hit enter, and I got 9. Now what happens when I ask it to do this problem? Of course, I'm going to do it in terms of x. When I ask it to do this, I'm going to hit math, 9. I want it to integrate 3 minus the square root. I hit the second and then the square root sign. Gives me a left parentheses. I can put in x minus 2, close the parentheses. So 3 minus the square root of x minus 2. I'm pretending that the variable is x, comma 2, comma 11. 3 minus the square root of x minus 2 with respect to x from 2 to 11. If I hit enter, it takes a little bit longer. Keep going. Doesn't exactly give me 9 as an answer. And this is something that I don't want to mislead you. You are not getting, there isn't a little man in the calculator who's anti-differentiating and plugging in. You are getting an approximate integration technique. You will learn about approximate techniques of integration in your calculus classes. Now, certainly to a few decimal places, this is 9.0, but right here we see it is not exactly 9. It is an approximation that the calculator is giving you. Okay, and this is something you have to be aware of. Of course, you may have no difficulty saying that these are really the same. Certainly when we did it by the fundamental theorem of calculus, we got exactly the same answer. Here, it's not exactly the same, but you may be satisfied with it. And that brings us to the end of this tape.